In this video, we're going to look at how to use logarithmic functions. So logarithms are the inverse of exponential functions. It's how we undo an exponential. So in orange here, you'll see an exponential growth function. And then remember that inverse functions are just reflections over the line y equals x, because to find an inverse, we just switch the x and y. So then if you look at this as a reflection line, you'll see that we create this inverse function, which is the logarithm function that we're going to be talking about here. So just a little bit of review on exponents. If you have a negative exponent, remember that's the reciprocal with the positive exponent. So just flip it to the bottom and make the exponent positive. Or if the negative exponent is on the bottom, you can just flip it to the top and make it positive. So 4 to the negative 2 would be the same as 1 over 4 squared, or 1 over 16. If you have a fractional exponent, remember that the number in the denominator of your exponent is your root. So you'd have the nth root of a to the m power. And that m can be put inside the root like that, or you can have it outside of the root like this, depending on what makes the most sense for the problem. So for this one, we would have the 4th root of 5 cubed. All right, then let's solve for x in each of the following problems. Let's start on the left-hand column here. So 3 to the x equals 9. What would x be? So we know that 3 to the 2nd power equals 9. So our x would be 2. 2 to what power is 32? So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 2 to the 5th power. And 10 to what power gives us 1,000? So 10 to the 3rd power. So then over in these ones in the right-hand column, these do not have whole number solutions. So we know that 3 squared is 9, 3 cubed is 27, and then 3 to the 4th is 81. So we know that in this, x is less or is greater than 3, but less than 4. So it's somewhere between 3 and 4. Here, 2 to the 5th was 32. So 2 to the 6th is 64. And then 2 to the 7th would be 128. So here we know that our x value is somewhere between 6 and 7. And in this last one, 10 squared is 100 and 10 cubed is 1,000. So we know that our x value is somewhere between 2 and 3. So this idea here, this is why we need a logarithm, so we can actually find the exact value of x that would make 3 to the x 33, or 2 to the x 100, or 10 to the x 120. So that gets us into the need for logarithms. So a logarithmic function, like I said earlier, is just the inverse of the exponential function. It undoes an exponential base to kick back our exponent. So there's a couple different ways we can write logarithms. So one is that we have y equals the log base b. So this is a little subscript down here, and this could be any number. So log base b of x. If we just see it written as log of x, the base here is a 10, so we don't have to write it. So if you just see log of x, the base is automatically 10. Just like if we just write a variable, we know the coefficient is a 1 and the exponent is a 1 without having to write it. So log of x just has a base of 10, and that's just understood. Then if you see this one, and this is ln, so the natural log of x, the base is automatically e. So this one is going to help us with base e functions. And so this is ln. So if you're thinking that looks like an I, it's an L. So then we have exponential form. Okay, so this is going to be where you have something equals a base to an exponent. So in this case, I just have it as x equals b to the y. So then the logarithmic form that goes with that, and we're going to practice rewriting in logarithmic and exponential form. But to undo this base, then we would have a log base b, and then we switch the input and the output since they're inverses of each other. So now this output becomes the input, and this input becomes our output. Okay, so if x equals b to the y, then log base b of x would equal y. So let's practice doing that. So we see in this first example that we have 7 to the third power equals 343. So that means that we're going to have a log base 7, okay, of the output. So log base 7 of 343 is equal to that exponent of 3. Here, so look for the exponential portion. So the exponential portion is 10 to the negative 2. So that's going to give us our base for our log. So log base 10 of the output. So log base 10 of 1 over 100 is equal to the exponent, or negative 2. 16 is our base in this one. So we'll have log base 16 of the output, which is 2, equals the exponent, which is 1/4. So that's rewriting from exponential to logarithmic. So then let's rewrite some logarithmic forms back to exponential. So you'll look for this base. So we'll have the base, and then we switch the input and output. So now we're writing an exponential. So this output of 3 becomes the exponent, and then this input becomes our answer. So 2 to the third equals 8. This next one, remember, is just a regular or common log. And so that's going to have a base 10. So we have 10 to the negative 3 equals this input of 0.001. And then this one is a natural log. So we know that the base is e. So e to the 0 power equals 1. So e to the answer equals the input. So e to the 0 equals 1. So based on this, there's a couple of properties we can look at. So log base b of 1 is always going to be 0. And that's because b to the 0 power equals 1. So any base, no matter what it is, to the 0 power will equal 1. So log base anything of 1 will always equal 0. Log base b of b will always equal 1, because in exponential form, this is b to the 1 equals b. So if you have the base and the input are equal, you'll kick back a 1. So then log base b of b to the y, it'll always kick back that y, because we would have b in exponential, it'd be b to the y equals that input, b to the y. And then if you ever have an exponential base to a log of the same base, so b to the log base b of x, it's going to kick back the x, because again, the log and the exponential base are inverses of each other. So like this b and this log base b are going to cancel, and it's going to give you back the x. Okay, or right here, your log base b and your base b are going to cancel and kick back that exponent, which is also what's happening here, log base b of b. And then same thing happens with the natural logs. Natural logs just have a base of e. So then we'd have e to the 0 equals 1. So the natural log of 1 is 0. The natural log of e is 1, since this base is an e. So then these would cancel and get you back that 1. This base is e as well. So the natural log of e to the y is going to kick back y. And then e to the ln of x. So the e and the ln will cancel and kick back that x. So these are just some properties of logarithms that we're going to be using. So let's evaluate each of these using those properties. So log base 23 of 1. Okay, so log base 23 of 1. Look back here. So log base anything of 1 is going to equal 0. Because this, we could look at writing it as 23 to the 0 power, and then we see those canceling. So you just get back 0. Log base 5 of 5. So the log base 5 and the 5 will cancel, and it'll kick back that exponent of a 1. Log base 2 of 32. So what we want to do is write this as a base 2 exponential so that we can cancel out the base. So 32 is 2 to the 5th power. So then the log base 2 and the 2 will cancel, and this will kick back a 5. Log base 4 of 1/4. Well, remember 1/4 is really just 4 to the negative 1. So log base 4 of 4 to the negative 1 will just kick back negative 1. So 1/64 as a base 8. So this is 8 to the negative 2. So log base 8 of 8 to the negative 2 is just going to kick back negative 2. So we see the base 5 here. So writing 1/125 as a base 5. So that's 5 to the negative 3. So log base 5 of 5 to the negative 3 will kick back negative 3. Natural log of 1/e². So remember, this is a base e. So we're just rewriting this as e to the negative 2 so that we've got the base e. So ln and e cancel, and we get negative 2. Log base 10 of 1. So remember, that's always 0, and that's because 1 can be written as any base to the 0 power. So 10 to the 0 is 1, so we could rewrite it like that, and then the log base 10 and the 10 canceled to get back that 0. Rewriting 343 as a base 7, so that's 7 to the 3rd power. So log base 7 and 7 will cancel, and we'll get back 3. In this one, we want the exponents, so we don't want any radicals. So we're going to want to use our rule of radicals to write this as a fractional exponent. So this is going to be e to the 4/5 power, because we know that this will come as the denominator of the exponent. So then the natural log and the e will cancel, and we'll just get back 4/5 as our answer. Now this one, the base is a 1/3. So when the base and the base here are reciprocals of each other, we know that that means there's a negative exponent. So this is 3 to the 1st. So if we wanted to rewrite this as the reciprocal of 3, we would rewrite it as 1/3, but to the negative 1 power. So a reciprocal, we would always need a negative power. So then the log base 1/3 and 1/3 would kick back our negative 1. And then log base 2 of the square root of 2. So rewrite the square root of 2 with a fractional exponent. So remember, that has a 1 here and a 2 here. So that's really 2 to the 1/2 power. So log base 2 of 2 to the 1/2 just gets us back 1/2. Then let's rewrite these logarithmic equations as exponential equations, but don't solve for x. So now we're just going to be doing what we did here, where we're just rewriting in exponential form. This time we just have a variable. So remember that if the base isn't written, it's a 10. So this one is 10 to the 3rd equals 4x. And again, we're not solving it, but 10 to the 3rd equals 4x. Here we would have a base of x plus 1. So this is going to be x plus 1 to the 6/7 power equals 4x. And then this last one has a base of e, since there's no base written for that, and it's natural log. So this is going to be e to the 3/7 power equals that input of 4x plus 1.